In the last two sections, we've looked at Riemann sums and have seen that they come up in a variety of physical applications. And in the next chapter, we're going to look at just a ridiculous number of applications of integrals, which is what we called limits of Riemann sums in the last section. We had limits of Riemann sums. We know that the definite integral, this limit of Riemann sums, is you take smaller partitions with arbitrarily small mesh. We know that that limit exists, or when it exists, we say the definite integral exists, and we know that that's true for continuous functions. We didn't prove it because it's too theoretical, but yeah, we know that for continuous functions, this definite integral that you should think of as a continuous sum of infinitesimal contributions exists. And yet, it's, in the last two sections, it's been very ugly to calculate such things. You actually have to take some partitions, maybe of where all the subintervals have the same width. That's slightly easier. But you actually have to take some, at least, sequence of partitions and sample sets, and you have to take the limit of Riemann sums and see what you get. This is painful. It's an ugly process. It's an involved process that's not very quick. You can, after we interpreted the integral in terms of area, if we had geometric formulas for the area under graphs or trapped between graphs and the x-axis, then we appealed to that to know what some integrals were, but we don't have that many geometric formulas for area, and also we'd kind of like to avoid appealing to just pictures in our proofs. So this section of the book is about the fundamental theorem of calculus, and it's called the fundamental theorem because it's absolutely fundamental. This is the big theorem, the biggest theorem in calculus. It relates the antiderivative, which has the same basic notation, right? The antiderivative of a function we write like this. The definite integral we write like this. Why do we write essentially the same notation except for the limits of integration? Why do we use the same notation for the antiderivative and for this continuous summing process? And the answer is the fundamental theorem of calculus, which links the two. So let me return to some things that we did see in the last section. So we saw that the definite integral from a to b of 1 times dx is just b minus a. And the definite integral of x from a to b of dx is b squared minus a squared, b squared over 2 minus a squared over 2. We saw that the integral from a to b of x squared dx is b cubed over 3 minus a cubed over 3. Let me write this, introduce some new notation and write these differently. We're going to introduce the notation that if we write a function and then write a vertical bar with an a at the bottom and a b at the top to the right, so it's not an integral sign, it's just a vertical bar. It's usually referred to as an evaluation bar. We're just defining this to mean take this top number, insert it into f, and subtract what you get when you insert the bottom number. This is very handy notation. We'll use it throughout. You use it throughout integral calculus. With that notation, this b minus a is the same as x evaluated from a to b. This b squared over 2 minus a squared over 2. With this notation, it's x squared over 2 evaluated from a to b. So I say evaluated from a to b, but that means you plug in b and subtract what you get when you plug in a. And this is x cubed over 3 evaluated from a to b. So if you look at these, what you see is, okay, the integral from a to b of 1 dx is x. Evaluate from a to b. The integral from a to b of x dx is x squared over 2, evaluated from a to b. And the integral from a to b of x squared dx is x cubed over 3, evaluated from a to b. If you remember your antiderivatives, what you see is, oh, x is an antiderivative of 1. Right? All that means is the derivative of x is 1. And x squared over 2 is an antiderivative of x, which just means the derivative of x squared over 2 is x. And x cubed over 3 is an antiderivative of x squared. So that, yeah, all that means is the derivative of x cubed over 3 is x squared. This is not a coincidence. This is the fundamental theorem of calculus, that if you can produce an antiderivative of the function that you're integrating, all you do is evaluate that at b and subtract what you get at a, provided that the function is nice enough, and nice enough means continuous. That's where we're headed in this section. We won't do a lot of applications because we're going to save those for the next chapter. But what you're for the next chapter, what you're supposed to get out of this is that this fairly ugly process, this limit of Riemann sums, suddenly becomes very manageable. All the formulas that we develop for antiderivatives now tell us how to calculate these continuous sums of infinitesimal contributions that we care about so much. So we have to, before I can state the fundamental theorem, even though I essentially said the main part over there, there are one or two other basic things we need so that we can give some idea of the proof, because it's not bad at all. So first, we want the mean value theorem for integrals. And what this says is, if little f is continuous on the closed interval from a to b, then there exists C in AB, so some x coordinate in this closed interval such that the integral from a to b of f of x dx is f of c times b minus a. This is the mean value theorem for integrals. It's actually the key step to proving the fundamental theorem of calculus, and yet it's fairly easy given the results that we had in the last section. Of course, we didn't prove our results in the last section, so I say it's easy, but modulo the things we didn't prove in the last section. So how do you prove this? It's actually surprisingly simple. Since f is continuous, the extreme value theorem from differential calculus, since f is continuous on AB, the extreme value theorem tells us that f attains a maximum value, which I'll call capital M, on AB. So there is some x coordinate in this closed interval from A to B where f of x is the biggest it ever gets. It's M. And attains a maximum value on, and attains a minimum value. Which I'll call little m. So what this means, i.e., for all x in AB, the value of f of x is somewhere between little m and capital M, and there are places where you hit each of these, little m and capital M. All right, that's a consequence of the extreme value theorem, but we know that the integral, the definite integral from A to B is monotonic, right? So, which means that because little m is less than or equal to f of x is less than or equal to capital M, the definite integrals of those functions, so these two constant functions and that function, over the interval from A to B, satisfy the same inequalities. So since integration is monotonic, since integration is monotonic, this implies that the integral from A to B of this constant little m is less than or equal to the integral from A to B of f of x dx is less than or equal to the integral from A to B of this constant capital M dx. But we know how to integrate a constant. Right? You can just pull the constant out, and the definite integration is linear. We can pull out this constant m, and it's just the integral of 1 dx. But then the integral of 1 dx from A to B is just b minus a. So we get m times b minus a is less than or equal to the integral from A to B of f of x dx is less than or equal to, and again, this is capital M times b minus a. Now, I've been assuming, I didn't say it, but I was assuming that a was less than b. In fact, if a equals b, the whole theorem is true and silly, because then the integral is 0 and b minus a is 0. So really the case that's of interest is when a is less than b, and assuming a is less than b, which I really should have said somewhere, assuming a is less than b, you can divide by b minus a, and you get that this quantity, this 1 over b minus a times the integral from a to b of f of x dx, is somewhere between the minimum value of f and the maximum value of f on the interval. But now we use the intermediate value theorem, right? F is a continuous function. Little f is a continuous function on the closed interval from A to B. And it attains the value little m somewhere, and it attains the value capital M somewhere. But the intermediate value theorem then says, by the intermediate value theorem, if you have a continuous function, and it attains two values, and you pick a value, you pick a number in between, then it also has to attain, there has to be an x-coordinate in the interval from a to b where it attains that intermediate value. By the intermediate value theorem, there exists C. In AB such that f of c equals 1 over b minus a times the integral from a to b of f of x dx. But now you multiply both sides by b minus a, and you get what we want. In fact, this is a nice way to write it, if a is less than b. But if you don't want to worry about that, you multiply both sides of this by b minus a, you get f of c times b minus a equals the integral from a to b of f of x dx. All right. That is the proof of the mean value theorem for integrals. Before I use this to prove the fundamental theorem of calculus, I'd like to look at this quantity for a few minutes. This quantity is usually defined to be, so I'm definitely assuming a is less than b. This is defined to be the average value of f on AB. So this quantity, 1 over the length, the width of the subinterval, times the integral from a to b of f of x dx is by definition the average value of f on the closed interval from a to b. Now, you'd probably look at this and you go, average value is supposed to mean the average value of some numbers. You add numbers and you divide by the number of numbers. That's the average value. This is some weird continuous sum and you divide by the length of some interval. In what way, shape, or form is this an average value in any sense that we're used to? So let me explain why it is the best notion, or a good notion at least, of average value on that interval. So we have to go back to what the definite integral means. It's a limit of Riemann sums. If little f is continuous, it doesn't matter how we pick our partitions, as long as the mesh approaches 0, then regardless of how we pick the sample sets, if we take the limit over some sequence of partitions whose mesh approaches 0, then that limit of Riemann sums will give us the definite integral. So what should the average value of f on AB mean? Well, okay, let's draw the interval from a to b, and let's chop it up into n subintervals of equal length, whichever you want to say. Right, so n subintervals. So I'm partitioning the interval from a to b into n subintervals of width. Well, the whole width of the interval from a to b is b minus a, but I want n subintervals of width. Well, then it would be, if they're all equal, it would be b minus a over n. So this is the width of each subinterval. Okay, suppose I do that. I chop up the interval from a to b into n subintervals of equal length, and then I pick sample points like we're used to. So I pick some S1 in the first subinterval, some S2 in the second subinterval, some S3 in the third subinterval, and so on, down to the Sn in the nth subinterval. All right, well, then what should kind of the average value or our approximation to the average value of the function be, considering this partition and that sample set? Well, now we have our real honest-to-God notion of absolute value. It is, I'm going to try to leave this up here, see if I can make everything fit. You would take the sum of, so the average value of f. So you take your sample points, you put them into f, you add those values. So we're looking for the average value of f. So we take each of those sample points, we put those sample points into f, so we get the values of f. And what should the average value mean? You add up those values of f and you divide by the number of the values. So that's n. So this is the average value of f over the sample points of our partition, of our sampled partition. So what should the average value of f on the interval be? Well, we'd like to take the limit of this as n goes to infinity. Right? We'd like to take smaller and smaller subintervals and take different sample points, and we'd like to know if this approaches a limit. And if it does, that would be a reasonable notion of the average value of f for a nice continuous function, the average value of f on the interval. And my claim is this does in fact equal the limit as n goes to infinity of this sum as I goes from 1 to n of f sub si over n, provided we know that the integral exists, which we know from the last section, that for a continuous function, the definite integral does exist. Why does this equal this? Actually, it's easy now because you just multiply the numerator and denominator by delta x. But delta x is a constant. It doesn't change with I. We're assuming all the subintervals have equal length. So if you multiply by delta x, you can distribute that over this summation. So you can put the delta x here and the delta x here. But then hopefully you recognize that as the Riemann sum associated with this partition. This is just you evaluate f at each of the sample points and you multiply by the widths of the subintervals. Great. Well, what's n times delta x? N times delta x, you multiply both sides of this by n. N times delta x is always b minus a. So that denominator is b minus a. And if you take the limit as n goes to infinity so that the mesh of the partitions is approaching 0, then this converges, this approaches the definite integral. Right? Because that's what the definite integral is, the limit of the Riemann sums as the mesh of the partition approaches 0. And we know it, if the definite integral exists, it doesn't matter how the mesh of the partitions approaches 0. So yeah, this is a reasonable notion of the average value of f on the interval from a to b. So what the mean value theorem says in this respect is that, okay, yeah, we had the b minus a on the other side of the equation, but what the mean value theorem says is if f is continuous on the interval from a to b, there's an x-coordinate c in the interval from a to b, such that the value of f there is this average value of f on the interval. Well, that's why it's called the mean value theorem. Mean and average are synonyms. So yeah, it's just saying, yeah, there is a point c between a and b where f actually attains its mean value. All right. So what does this have to do with the fundamental theorem of calculus? Pretty much everything. Let me remind you of a definition. So antiderivative. You know, I want to be very careful and talk about the antiderivative of a function on a closed interval. And normally we wouldn't talk about derivatives of a function On a closed interval, you need kind of open intervals so you can take a little smaller value and a little bigger value. So suppose f is defined on a closed interval. So its domain contains the closed interval from a to b. Then another function, then f is an antiderivative on this closed interval. Right, so this is a definition. I should have written that. This is a definition of antiderivative on a closed interval. Is an antiderivative of little f on the closed interval from a to b if and only if we want f to be continuous on the closed interval. We know what that means. And then on the open interval inside of AB, so the open interval from A to B is continuous on AB, and for all x in the open interval from A to B, f is differentiable at x. And f prime of x is little f of x. So f is some function whose derivative is little f of x. Don't get this confused. We are not differentiating little f. We are anti-differentiating it. We are finding where capital F is some function whose derivative is little f of x, at least on the open interval from A to B, and we also want capital F to be continuous on the closed interval from A to B. All right. With this terminology, and having the mean value theorem for integration, I can state and prove the fundamental theorem of calculus. The fundamental theorem of calculus. It has two parts, and it's the second part that people use most of the time. But the second part follows very quickly from the first part. It's the first part that's kind of the guts of the theorem. It's just hardly anybody uses this one. One, the function, so suppose f is continuous on AB. Then, one, the function, this is going to be ugly, or weird looking, the integral from A to X, here, the function, let's call it g of x, equals the integral from A to X of f of t dt is an antiderivative of f on AB. Understand what this function is. So I'm using x for my independent variable because we like to use x for our independent variable. And it's now one of the limits of integration. So this function, you put in different x's and you get different integrals. But those integrals exist because we're only using x's in a b, so that a and x would be in the closed interval from a to b. F is continuous on that interval, so we know that the definite integral exists, but we're changing the interval over which we're integrating. Since we put x up there, it would be bad form to use x as our dummy variable, so we switched to a t. We could have used a u. We could have used essentially anything other than a, x, and b, and f. D would be a bad choice too. It's just a dummy variable in the definite integral. The actual variable that has to do with the function is there in the limits of integration. So the function is an antiderivative of little f. That means that the derivative of this function, the derivative of integration, is this little f. So this looks bad when you write it, or it looks, I don't know, it either looks bad or it looks silly when you write it in prime notation. So you will see some books write things like, so knowing that this prime means the derivative with respect to x, well, this is supposed to be an antiderivative of f. So what's the derivative of this? Just little f of x. And so, yeah, if your lower limit of integration is a constant, your upper limit of integration is an x. What this main part of the fundamental theorem says is that when you differentiate this function, it just looks like all you did was stick that x into the integrand. That's the first part of the fundamental theorem of calculus. It's a bit much to absorb. We are going to prove this because it's so essential to the second part, which is what we want. The second part of the fundamental theorem of calculus is the one that gets used all the time. 2. If capital F of x is any antiderivative of little f on AB, I guess I should be consistent, not write that of x on AB, then the integral from a to b, and now I'm free to use x again as my variable, but I won't, just to make it look like that. But this dummy variable, it's a t. I could put in x here and here, because it's not over here in the limits of integration anymore. But as I said, this is a dummy variable. It doesn't matter. This is f of t evaluated between a and b. That means f of b minus f of a. This is what I said at the beginning. If you know an antiderivative of the function, you simply produce it, evaluate it at b, subtract what you get at a, and that gives you the value of the definite integral. This is the fundamental theorem of calculus. Before I show you why these are true, I want to emphasize that students tend to forget that the fundamental theorem is a theorem and that the definite integral doesn't mean anti-differentiate. The definite integral, the reason it comes up in so many applications is because it's this continuous sum of infinitesimal contributions. And the reason it's the continuous sum is it's the limit of Riemann sums. So essentially all of the applications come from the definition of this as a limit of Riemann sums. The fact that you calculate it by taking an antiderivative is the fundamental theorem of calculus. And it's extraordinarily important if you just start thinking that the definite integral means the antiderivative with the top limit of integration stuck in it minus the bottom limit of integration stuck in it, you miss out on understanding all of the applications of the definite integral. It is a continuous sum of infinitesimal contributions, but you calculate it by producing antiderivatives. This is the fundamental theorem of calculus. All right, why are these things true? Let me show why this part that we use so much follows quickly from the first part, and then I want to show how the mean value theorem quickly gives you the first part also. So suppose we believe part 1 of the fundamental theorem of calculus. Why is this true? And the answer is because, as you should have seen in Calc 1, any two antiderivatives of f on AB differ by a constant. What does this mean? If g of x and f of x are antiderivatives of little f of x on some closed interval, then there exists a constant C such that f of x, or how about if I write it the other way, g of x equals f of x plus c for all x in AB. Right? You know this, right? It's why when we produce an antiderivative, the general antiderivative of x dx, the antiderivative of x with respect to x, is x squared over 2 plus a c, because what do all the antiderivatives of a given function look like? They all look like one antiderivative and then plus a constant. That's, I'm reminding you of that. Any two antiderivatives of this function on AB differ by a constant. Okay, so you know this, but that's why this follows from part 1, because part 1 tells you that the integral gives you one antiderivative, and if you've got another antiderivative, they have to differ by a constant. So what does that say? So suppose we have some antiderivative that we produced by one of our antiderivative formulas, maybe. Suppose f of x is an antiderivative of f, or on AB. Well, the first part of the fundamental theorem says that integral is an antiderivative. Then, so they must differ by a constant. Then, that tells us that this integral, which is one antiderivative, must equal this other antiderivative plus a constant. This is for all x. In AB. Okay, so why does that tell us what we said before? Well, there's one value of x that you can plug into this formula that will tell you what that constant c has to be. namely x equals a, because then we know that this side is 0. The integral from a to a of f of t dt is 0. So we plug in x equals a. When x equals a, we find 0. 0 over here equals f of a plus c. Put the f of a over there. So c is minus f of a. Oh. So c is minus capital F of a. That was very bad. Don't do that. You put that back in, and what we get is the integral from a to x of f of t dt is f of x minus f of a. This is true for any x in the interval from a to b, in the closed interval from a to b. In particular, you can replace the x by b, and you'll get this, which is what we wanted. That if you have some other antiderivative, you just evaluate it of the function that you're integrating. You just evaluate it at the top limit of integration, subtract what you get at the lower limit of integration, and that gives you the value of the integral. Cool. All right. So now our question is, why is the first part of the fundamental theorem true? Why does this awful, I say awful because understand how bad this is. This function, for each x coordinate that you pick between a and b, this is some limit of Riemann sums. And as you change x, you change your interval, and you have to, it's a whole new limit of Riemann sums. And awful if you unravel what this says. But the mean value theorem for integration actually makes this first part easy to prove. So what is it that we would like to see? I want to show you that the derivative of this function at a point in the open interval from a to b is in fact f of x. I'm not going to verify that it's continuous. That's a technical result. But I'm not going to verify that it's continuous. Of course, if it's differentiable, it's continuous. But that won't tell us it's continuous at a or b. It's true, but that's technical. But I will verify that the derivative at an interior point, so a point in the open interval from a to b, is just f of x. This is surprisingly easy. So we have g of x equals the integral from a to x of f of t dt. I want to show that g prime of x is just f of x if x is between a and b. So g prime of x is by definition the limit as h approaches 0 of g of x plus h minus g of x over h. Right? I'm assuming that x is in the open interval from a to b. Okay, well, what is this? This is the limit as h approaches 0 of the integral from a to x plus h of f of t dt minus the integral from a to x of f of t dt, all divided by h. That may not look very nice, but that numerator actually simplifies greatly. This is the limit as h approaches 0 of, that numerator is just the integral from x to x plus h of f of t dt divided by h. Why is that? Why is this the same as that? It's because of how we can split integrals, which we talked about in the last section. That if you, so really we're reading, I'll erase the, let me write it over here. What I just used was that if you integrate from a to x plus h of f of to x plus h of f of t dt, you can split that as the integral from a to x of f of t dt, plus you can pick it up at x and go to x plus h of f of t dt. Actually, those are too close together. That looks very confusing. Plus the integral from x to x plus h of f of t dt. And what I used is exactly this equality with this part subtracted from both sides, so that the integral from a to x plus h minus the integral from a to x gives you the integral from x to x plus h. I should remark that we, of course, need for these limits of integration to be inside the interval, the closed interval from a to b. For the integrals, for us to know the integrals are defined. So x is something in the open interval from a to b, and you only do this for h small enough so that x plus h is still inside the interval from a to b, which you can do because x is in the open interval. So there's some distance between x and a and between x and b, and you take h smaller than those in absolute values so that x plus h doesn't go outside your interval. So we're taking the limit as h approaches 0, so we can certainly assume that h is small enough to stay inside, to make x plus h stay inside our interval. So this becomes this. So now we use the mean value theorem for integration, which said that numerator equals, well, it equals the f evaluated at some c, at some x coordinate between here and here. So, so we get f evaluated at some c. I'm going to subscript it with an h to indicate that c depends on what h is, this c sub h, times, well, before it was b minus a. It was the upper limit of integration minus the lower limit. But then the x's cancel, and it's just times h. This is where c sub h is in. And it's either, it depends on whether h is positive or negative. So it's in, if x is positive, c sub h is in x comma x plus h, that open interval. Or if h is negative, it's in this open interval. Okay? The h's cancel, and what you get is that this equals the limit as h approaches 0 of f of these c sub h's. What is this? Yuck. But look at it. C sub h is trapped between x and x plus h, on one side or the other. As h approaches 0, c sub h doesn't have a choice. It approaches x, because as h approaches 0, this subinterval becomes closer and closer to, well, gets to be a smaller and smaller subinterval. I should have had the closed interval here to match what I wrote for the mean value theorem. Sorry, closed interval from x plus h, or closed interval from x plus h to x. As h gets closer and closer to 0, this closed interval just becomes closer and closer, being the closed interval containing just x, or the interval gets smaller and smaller. The c sub h's are approaching x. So the c sub h's approach x as h approaches 0. But f is a continuous function. If c sub h approaches x, then f of c sub h approaches f of x. And so this limit is f of x, since f is continuous. And that's it. That's the fundamental theorem of calculus, that the derivative of this function is just what you get when you stick that x into the integrand. Throughout the book, when we calculate integrals, we will use the fundamental theorem. We will use our antiderivative formulas to produce antiderivatives of functions, and then to calculate integrals, you just insert the top limit of integration and subtract what you get at the bottom limit of integration. Things are very easy for us now. As I said, we're going to have a whole chapter of applications, and they'll be interesting and they'll be informative, and it will show you the value of integration. But right now in this section, I'd just like to quickly calculate an area as just an example of how easy things are for us now. So suppose, for some reason, you want, here's the graph, this is supposed to be the graph of y equals 1 over x. Maybe, for some reason, we want to find the area under the graph of y equals 1 over x between above the interval between x equals 1 and x equals 3. So the question is, what's that area? There aren't any geometric formulas that you learned in middle school or high school that are going to help you with this. It's, what is it? Well, it's a limit of Riemann sums that give us the area. You add up all these little infinitesimal rectangles. Well, yeah, but we know what it is in terms of integrals. It should be the integral from 1 to 3 of this function, 1 over x dx. We discussed this in the last section, that if you take a positive function or a non-negative function, the integral, if it exists, will give you the area under the graph and above the interval that you're interested in. Great. So how do you calculate that? In the last section, or the one before it, we would have had to have taken we would have had to take partitions and take a limit of Riemann sums, but now we don't have to. We produce some antiderivative of 1 over x on this interval from 1 to 3. Well, antiderivative of 1 over x, natural log of the absolute value of x. Our x is always positive. We don't need the absolute value signs. The natural log of the absolute value of x. And then you just evaluate that from 1 to 3, which means you put in the top limit of integration and you subtract what you get at the bottom limit of integration. We know the natural log of 1 is 0. This is just the natural log of 3. And that's it. That's all you do. There are no partitions, no sample points, no Riemann sums, no limits. This is how we're going to calculate definite integrals from now on. But it's important to remember that the fundamental theorem of calculus is a theorem, and that this definite integral, by definition, is a limit of Riemann sums, and that's what makes it a continuous sum of infinitesimal contributions. It's a theorem that you calculate it by taking an antiderivative, but you need to not think of this inherently as an antiderivative. Yes, I'll say it for the, 5th time. Yes, you calculate it by producing an antiderivative, but that's not what it means. It means the continuous sum of infinitesimal contributions. All right. In the next chapter, we will get to a whole bunch of applications of this. Before we do that, we need a couple of more theoretical things, and then we want to talk about some numerical techniques for approximating integrals for functions that we can't produce antiderivatives for.